So this lecture is going to be focused on what I like to call fundamental interactions. And these are the interactions that you're going to find in physics that we can study between objects, massive objects, and also between particles, between the Earth and the Sun, between protons and neutrons, between electrons and photons. So there's lots of different things that are happening on all different scales, and physics has good ways of understanding and modeling how those things work. And so in particular, we're going to be focused on the fundamental law of gravitation. All of next semester, actually Phys 102, is concerned with the electromagnetic phenomena. There's also particle physics, which deals with the strong and weak interactions. The standard model of particle physics, one of the big discoveries recently at CERN was, of course, the Higgs boson. And there's been a lot of work that's been done in understanding fundamental physics at the very small scales and how matter is basically put together. But we're going to talk about the larger scale effects, so the implications of gravitation and how that all looks from our perspective. Okay, so we deal with gravity every day. We are pulled towards the Earth by it having a mass and us having a mass. So the force of gravity it is a force between two bodies. Any two massive bodies. These are objects that have mass. And it is always attractive. It has been experimentally determined to be proportional to the square of the distance between the bodies. Now this is amazing. It's not something to the 2.00001 power or even the 2.000000001 power. It is something to the 2 power. And that's fundamental to the nature of the way the universe is put together. If gravity was different than a square, we would be living in a very different world. Okay. Now, let's write down what we know about the way gravity acts on two bodies with mass. So I'm going to draw two bodies, two objects. Object 1, object 2. I'm going to separate them by distance given by r, which is a vector. So this vector is going to separate the centers of these two objects. So here's a line along the center, here's a line along the center, and the vector between them is going to be r. I'm going to call this one mass 1 and this one mass 2. And it's important that they have a mass. And we need to write down a convention for the way that we talk about the way that the force acts between these two objects. So I'm going to say the force on object 2 by object 1, on 2 by 1, so the force on 2 by 1, so this is the force that this object feels due to the presence of this object, is going to be equal to, and I'll write it here in mathematical form, attraction in physics means negative, so the force wants to pull it in. G is a number. This is called the universal gravitational constant. The mass of object 1, the mass of object 2, these are multiplications, over the distance between them squared r hat. So it's a vector. So let's look at what we know. We know this is a vector quantity, and we know this is a vector quantity. I'm going to couple together my minus sign and my r hat. So which direction is minus r hat? On 2 by 1. So on 2, the force acting on this object points toward the center of 1. This is minus r hat. And the force is proportional to that. So I'm going to say my force is proportional to a constant times r hat. Here's force 2, 1. It's in the direction of minus r hat, and it points from the center of this object to the center of this object. That's my force. Okay? So I'm going to put my origin here. So here is 0, 0, 0. This distance is, of course, r to mass 1. This distance is r to mass 2. And so that's the way I define my coordinate system. And this vector here is the difference between these two vectors. So I can very easily find r hat and r. So r vector is just equal to r. So the difference between these two, right? So r2 minus r1. That's that vector. And r hat, of course, is just equal to r over the magnitude of r. Okay. Now, let me introduce some constants. G is equal to 6.7 times 10 to the minus 11 newtons meter squared per kilogram squared. Okay, so that's the gravitational constant. That can be determined experimentally. Like we said, r vector is the difference between r2 minus r1, and r hat, of course, is the direction of that vector. Okay. Now, this force has some interesting factors that we have to concern ourselves with. So let's take away some of the scribble. And what do we have? We have the force on mass 2 by object 1. It has a proportionality with distance, the distance between them, that looks like 1 over r squared. So if I want to know what the force is, the value of the force, the magnitude of the force, it depends. So this is the force 2, 1. This is the distance r between them. Right, so the magnitude of the distance. And the value of the force drops as a function of r. This, the form of this goes like 1 over r squared. Okay? So what that means is for short distances, as these two things approach each other, short distances, the force goes up dramatically to the point of contact where they're touching each other, and then it falls off rather quickly as you get further away. Okay. So what this says is that as the distance doubles, as the r gets larger by a factor of 2, the force goes down by a factor of 4. So it's a rapidly decaying force.